This happened in Grand Forks, North Dakota. They found the hard way the importance of confidence intervals. In April of 1997, the Red River flooded into Grand Forks. There was no loss of life, but about 50,000 people had to be evacuated. About 75% of homes were damaged or destroyed, and cleanup costs were estimated to be about $4 billion. All of this, however, was preventable. The reason they couldn't was because of a failure in communication. See, the previous winter, 8 blizzards dropped a whooping 98.6 inches of snow, which is a lot. And eventually all of that snow would melt and cause the water levels to rise, which would cause the flood. Now, the National Weather Service was equipped to make predictions about this because they had all of that past data and they have supercomputers. So using past data, mainly this amount of snow causes this amount of water, that kind of data, right? So for our purposes, that would be sample data. So using sample data, they made a prediction of 49 feet, that the water levels would rise to 49 feet. So they communicated this to the town and they prepared 51 feet levees. The waters rose to 54 feet, however, and the town was flooded. The problem was that there was actually a margin of error of plus or minus 9 feet. What this means is the following. The 49 feet that was predicted was only a point estimate. What that means is that 49 feet is just a point, just a number in the number line. What the margin of error of plus or minus 9 indicates, however, is that there was actually not a point, but an interval of estimates. And that interval goes from 49 minus 9 to 49 plus 9, which means from 40 to 58. So why was this not communicated properly? Well, there could be many reasons, we do not know, but I will say this. People love point estimates. The media loves point estimates. They will write headlines with point estimates. Intervals, not so much. But we just learned their importance. So let's say that I'd like to estimate the size, the average size of a home in all homes in Lake County. So we had this data, remember, for it was a sample of homes that were recently sold, and I have this variable which is the square footage for each home in the sample, and find their average. So this will be our sample average, right? Sample mean. And also I'm gonna need in the future, I'm gonna need the standard deviation. So might as well find that now. Sample standard deviation, because this is a sample. So I find the standard deviation using this. Okay. Alright, so the variable of interest here is square footage. That's our random variable. And the population is all homes in Lake County. The parameter is the true average square footage of all homes in Lake County. So in other words, if we were to add all the square footage for all homes in Lake County and divide by the number of homes, that would give us mu, but we do not have the data for the entire population, so this mu we do not know. So we're going to estimate it using a sample of the 179 homes that have reported a square footage in our sample. Okay, and so we found our sample mean, which would be the statistic, and now we want to use this number to estimate mu, but remember this number is just a point estimate. We want actually a confidence interval, and in order to build a confidence interval I need a margin of error. So to learn how to build a margin of error, we would need to first place our x bar in some distribution. So which distribution does the sample mean belong to? How does the distribution of all sample means look like? So where does x bar go? Well, we learned this not so long ago, right? Because we learned that all x bars are distributed like this. If it was possible for you to collect all possible samples of 179 homes, the sample means would look like this, would be distributed this way. This is called the sampling distribution of the mean. And we also learned that it's centered at mu, which is precisely what we're trying to estimate, right? So we centered at mu, and each of these gaps is this, sigma over square root of n. So that's what the central limit theorem tells us. So in other words, we have this. Now, mu is what we're trying to estimate. And how do we estimate mu? Well, we estimated with an x bar, right? And we found one of these samples. This is all possible samples, but we found one of these, and hopefully that x bar that we found would be there, because that would be perfect. But there's no guarantee of this, because a sample is always random. Well, this is a random sample, so these also could happen. So how could this happen? This could happen if we happen to pick for our sample, just because of some dumb luck, we happen to pick the smallest homes, the homes with the smallest square footage in Lake County. Then our x bar would be one of the smallest possible, which would be a serious underestimate of mu. Or something like this could happen, where we have an overestimate. The homes in our sample are above average in size. Okay, but so how do we know? We're uncertain where x bar would be, but we do know something because of a shape. We know that it is more likely that our sample mean is close to mu than that it is not, because the peak is in the middle. So in fact, we can put numbers to this, because based on the empirical rule, we know that there's a 68% chance that our sample mean is within one of these, meaning within one of these, okay, of mu. There's a 95% chance that our sample mean is within two of these of mu. So somewhere between here and here. So within two of these of mu. So there's a 95% chance that x bar is within two standard deviations. By standard deviations here, I mean these, right? Not sigma. But now, if I'm within 2 feet of you, you're within 2 feet of me. Okay, so I can switch this around. So instead of saying x bar is within 2 standard deviations of mu, I'm going to say mu is within 2 standard deviations of x bar. So in other words, in our picture, I can put x bar in the middle now, okay, and mu is within 2 of x bar. So even though this is not the exact picture of the sampling distribution of the mean, so this is not an accurate picture, it's a useful picture for calculations. So now I can say more precisely that there's a 95% chance that the margin of error, which remember is the gap between the center and the endpoint, this endpoint or this endpoint, so there's a 95% chance that this margin of error is 2 standard deviations, which more precisely means 2 of these. So we're going to call these standard errors. So we're going to say 2 SEs. Now, some terminology. This 95%, if you think about it, is optional. It's an option, right? You can pick any number you want. You can pick 90% if you want, although 95% is considered default. This is called the confidence level. Alpha is the opposite of a confidence level. So it's 1 minus the confidence level. So in the picture, alpha is the total wide area. But since this is symmetric, each of these is alpha over 2. Now there's a significance to alpha over 2, okay? In order to compute our confidence intervals, in order to learn more in depth about confidence intervals, we need to learn about critical values. A critical value is simply the z-score that corresponds to that alpha over 2. So in other words, since we're looking at z-scores, we need to look at the standard normal distribution, which is called the z-distribution. And it looks like this. So remember that these are the z-scores, and the standard normal distribution is this. And for a 95% confidence interval, the z-score at least by the empirical rule, the z-score, meaning the critical value, would be 2. The right critical value would be 2, and the left critical value would be -2. But this is only an estimate using the empirical rule. More exactly, using technology, it is approximately 1.96, so close to 2 but not quite. So now I put 0.025 here because that would be alpha over 2, right? That would be 2.5%. For a 95% confidence interval, alpha would be 5%, okay? So, and half of alpha would be 2.5%, so that's why I put 0.025. So now we can calculate this. But in order to calculate the confidence interval, I need to know what is sigma. Unfortunately, we do not have sigma because sigma is the population standard deviation. And if I want to calculate the population standard deviation, I need the population data anyways. But I don't have it. So instead, we're going to estimate sigma using S, which is the sample standard deviation. So we're going to assume sigma is 1284.69, which was S. And then we have this, the critical value for 95%, and we have the standard error is sigma over square root of n, okay? So in other words, sigma is going to be this, and then divide by square root of that, and then now the margin of error is how many standard errors is, the margin of error is this gap, right, which is z alpha over 2, the critical value, times SE. So we're going to denote the margin of error by E, is z times SE, which is that, which just gives you this. So now the margin of error is this, which means to find the confidence interval, I just add and subtract this to the sample mean. And we find this. Now we still have to deal with the fact that I assumed sigma to be S. Alright? It turns out that I can do that in this case, but I will show you that most of the times you can't. Now, William Gosset was an English statistician, and like everybody else, he also used S in order to estimate sigma using the normal distribution. What he found though is that when he used the normal distribution, it didn't work out when you substitute S for sigma. If you want to substitute S for sigma, you need a different distribution, and he called it the T distribution. And the T distribution is actually many distributions, a family of curves. And which curve you use depends on what we call degrees of freedom, which in this case would be the sample size minus 1. So for example, T2, which is what we call a T distribution with 2 degrees of freedom, would look like this. So notice it's very similar to the normal distribution, but not quite. And let's compare the actual values. So remember, for a normal distribution, the critical value for a 95% confidence level was 1.96, close to 2, but it was 1.96. Well, for a T2 distribution, using technology, we find that the critical value for 95% is -4.3 and 4.3. So again, I have that 0.025, but I'm using a T distribution now with 2 degrees of freedom. Okay, let's look at T8 now. So notice that it's a little better, a little closer to the normal distribution, but for the critical values for 95% confidence level, now we find it's a little closer to 1.96, it's 2.31. Now in our example, we would have to use T 178 because our sample size was 179. Notice that now, for really large sample sizes, it looks very close to the normal distribution. And the critical values are 1.97, which is very close now to 1.96, which is why for a large sample size like that, I was allowed to use simply the normal distribution when substituting S for sigma. So in summary, you use the T distribution instead of the normal distribution when we do not know the population standard deviation sigma and the distribution of X is normal. X here, by the way, means the population, right? Not the sampling distribution of the means. When the sample size is large, we do not require this normality condition. And for large sample sizes, using the t-distribution and the normal distribution yields similar results.